All right. Hi, everybody. My name is Greg Talbot. I'm going to share my screen here. All right. So let me get here to the beginning of the slideshow. So let me tell you a little bit about myself. I'm Greg Talbot. I'm happy to share the topic here of relational data. And myself, I'm a business intelligence manager. I work for a financial firm in Chicago and work with data quite a bit. So I'm really excited to explore this data, especially within the topic of R, the programming language R. So I do have dual monitors here. I'm going to look here at the camera, but also to my notes here. So I hope that's not distracting. But yeah, let's jump on in this. This is going to be reviewing data instruction from a book called R for Data Science by Hadley Wickman and Derek Grelumend. So let's dive in. All right. So we're going to talk about a few different areas today. We're definitely going to talk about relational data. And one place we can start is what do we think of when we think about data and data sets? We might look at something like an Excel spreadsheet or tables of columns and rows. But it's important to think that when we do data analysis, we're looking for more than one entity. We're looking for the relationships between entities of structured data. So for robust analysis, we want to look at the collective total of tables. We want to look at the relationships. Simply put, we need to think about relational data, and let's think about some of our definitions. So relational data, we can think of this as collective data. We have defined data between pairs of tables, and no matter how complex this data gets, it's going to be structured. And a fundamental idea, of course, is that we have data elements. These are maybe attributes specific to a data. So when we look at a record, the elementary, item about a data record might be a customer. We might look at for name and for age, for address. So we're pulling all the related data for that customer. And of course, within a table, we might have like a group of customers. So we can start to think about data in that manner, building it up with different entities, different tables that we can relate. We also want to talk about, I wrote down here, RDBMS. So this is the Relational Database Management System. This is basically the processing tool used to query the relational database. How do we pose a question, we script a question, how do we pull back the data set that we're looking for? So what are some of the actions that we can take on a table? Well, we can add data to a data frame. We can filter out our observations. We can, essentially use like a where clause to remove observations that are not needed. We can use what we call set operations. And set operations, these will combine different tables together to make a larger group of data, maybe an aggregate of these 2 or 3 tables as an example. So these concepts of joining, filtering, these are going to be very common within SQL, SQL. And here we're going to look at their expression within a function called dplyr. This is unique to R. So we're using dplyr, and it's because it is an R package used for data manipulation. And usually this will be a little more user-friendly. This is one of the prospects of R. It's often used in the academic settings as well. All right, so let's look at, let's explore the data. We'll look at 2 different packages here. We have 2 different libraries. There's Tidyverse and this New York City flights data. So let's first look at the New York City flight data. I'm just going to see if I can move. I have a little cursor here. I just want to move this down. Let's move this. Sorry, just one moment here. Okay, hopefully that doesn't show up on the video, but just so you can see the heading, I'm just going to move this little cursor, which is showing on my screen. So here we're going to look at what we call 4 tables or 4 data frames of data. If I look at it here, we have the airports and weather, airlines, and planes. But let's just look at one. So to a non-technical person, you might think about a data set similar to an Excel spreadsheet. That's certainly how I would describe it. Here we have different records for the plane. We have data related to the plane, such as the tail number, the year, the type, the manufacturer. This is a different table here called weather. and whether we have different records that could be helpful. The looks like some date time related data, so years and months, days, hours. We also have some identifiers for temperature, dew points, humidity. So when we look at the data, sometimes we might ask ourselves questions like how this data would interact, right? And of course, part of it too is the database. We don't want redundancy. We just want records which is unique to that for these different tables. So a lot of times when we're looking at these tables, we need to think about how the questions we're going to ask, the data narrative we're providing, what we're trying to get out of here. But let's go a little deeper. We can look at the programming here. Each data frame will have unique attributes. Let's run through an example with the airlines table. See if I can pull that up here. Okay, oh, here we go, airlines table. So when we look at the top, we have the number of rows and columns. We have a 16 by 2 matrix here. And each record will have an integer next to that record. Oh, very sensitive mouse, sorry about that. So we are looking at this table for airlines, and each record has the integer next to a symbol. Our 2-digit columns are a 2-digit identifier and the name of the carrier. So one example, we have AA, which is for American Airlines, as an example, which may not tell us too much on its own, but as we start to query some of these tables, joining tables together to make a unique data set, we're going to see how we can use that data. So additionally, we have tables for the airports here. This is the second table here. This includes data such as the name, longitude, altitude, latitude as key elements. Additionally, we have a table for the planes, as mentioned. This includes the manufacturer, engine, seat, and engines. Whatever details we're having that data discussed, humidity, direction, speed. So as we take these tables and data frames, we think about the relations between them. And I think that's a good point to just maybe pause the video, take a look at what we have here. We can visualize the relationship here between our tables. We do have the center column of flights, and we can see that this might be a way to join some of these tables together. So we're going to see some of the same elements, for example, tail number, which is on the flights table, as well as on the planes table. Another example is airlines. We have carrier as a key, which is also on the flight key. So we can start to think about how we relate these tables together. We start to actually think of this as a picture or a visualization of a system. Sometimes we see this in process mapping, just think about the way these different tables might work together. So we need to look closer, see relationships between the entities. And I think it's important too, look at these entity relationship diagrams. We can look at the directionality between them. So we might say, discuss this in terms of the airport data of the flights. So, the flight might be our primary entity, and we have the data from airports feeding into it. We see all the data is actually directionally towards the flights table. So this would be an indicator. This is one of our key tables that we use when we do our left joins, and we start talking about combining our different data from the tables. This is going to be a helpful way to think about how does this, what's the navigation of this data, how does it relate exactly. So we have some of our critical entities here. We've talked about airports, planes, flights, and airlines. And it's good to remember this will not be all the tables. We're going to have additional reference tables, smaller tables, things that kind of fill in the larger picture. But this might just be a very elementary way to think about all this data together. Let's look at the critical elements. We have a relation. A relation has a pair of tables. So let's consider relations between our tables here. We have, as mentioned, the flights connecting with the variable tail number. That was when we discussed. Let me see if there's some other ones here. We do see multiple variables connect, such as flight and the airport. So we're talking about the origin and the destination variable. We can think about, of course, we're thinking about the business processes as well. This is one view of our customer data, it looks like, but we need to think about the overlying business processes as well. How does someone, buy a ticket to an airplane? What kind of weather do they look for? The seasonal weather patterns that occur. That might be helpful when we're looking at data and start doing some analysis work. So this is our blueprint, our variables, but it may not tell the whole story. And we need to ask questions. Other questions we could ask are, how do we route a plane from a departure to a destination? Mentioning about seasonality, what additional weather detail could be helpful for airports, just to think about cancellations or the steps they have to take to make sure that we're able to get people onto the planes and to their correct destination. That's something we need to think about. So yeah, let's talk about the next step here. Oh, this is relationships between tables. But let's talk about keys. So keys literally are they're the keys to thinking about how we match up records between tables. So keys are variables used to join pairs of tables. Key is a unique identity to an observation. Sometimes we use a single variable like a identifier. This could be just a random number generated as a key sequence number to a table. But other times we'll have a composite key. So this might be an observation with multiple columns to basically identify this record as unique. So we're going to talk about two different types of keys here. We're going to talk about primary keys. These are unique observations to a table. We're looking at the plane data, for instance. We were talking about a plane tail number as a unique identifier of data. Let's go back here to show you that. Here we could say this is, and some of our mapping may well show like PK, primary key, or a foreign key for some of these variables here. So our maps can be very robust in that sense too. So yeah, primary keys, they identify the unique observations. Foreign keys, these are unique identifiers of observations in another table. So if we found that same example, planes tail number in the flights table, we would have the tail number here as the foreign key. So those are the two ways, and we're always thinking about in relation to these entities, which is relating to which is the primary, which is the foreign key. It's all relative to our view of the data. So as a validation check, we may want to do a count of records based off a grouping of the primary key. Let me see if I have here we can do this count here for flights, and we're looking at a flight, the count of flights in that year, month, day, and in flight, seeing if it's greater than 1. So this can be used as a validation check. So we might run into situations where we don't have an explicit primary key. Let me just. Okay, I'm just going to pause the share for one moment here. Okay, so I just wanted to pause there because I did want to clarify a point that you can have a variable being both a primary key and a foreign key. Let's look at that variable origin if we go back here. So here we see it in both, and right, it might be a primary key in the weather table, a foreign key in flights. So we looked at a few of those already, but I just wanted to clarify, it's not an absolute term. Your primary, your foreign key, it's just depending on the relation between the data. So that's one way to think about this. And then when we get back to our validation, it's important to mention, like, as a consumer, we might think that the flights are unique numbers. Flight number by itself, think, okay, there's a unique flight number, but that's the reason why we're including this other year, month, and day data, because you're going to see a lot of recycling of those same flight identifiers. And so when we think of that composite key, we're going to want to have all that data available to us. So that's critical. And of course, when we look at using the R language, we're going to want to use both functions like the mutate function, the row number. That's going to be helpful for matching observations, and then of course filtering to the exact data set which is needed. So what we look at here is we might have what you call a surrogate key. So not a explicitly defined key, but one that is a surrogate key. And then once you have that primary key, that relation between two tables, you then have, if we go back to our visual here, we then have a relation. This is a relation between our two entities. So we have that. We'll talk about the validation a bit. Also, you might say that, the relationships between tables are can be one-to-one, they can be one-to-many, they can be many-to-many. So you're going to see that in databases where you might need a reference table to link two tables. For example, you might have two entities like customer data, and then you might have the product data for a customer. Here we're talking about flights. So it's interesting to think about the different ways that those tables might relate to each other, maybe through the shipping address or some relationship that matches data between the customer and the product. So let's move forward here. Let's talk a little bit about mutating joins. So the first thing to say about mutating joins is that this function used, this mutate, will be used when we combine pairs of tables. And it first matches observations by their keys, and then we copy across variables from another table. So with this mutate join, the join functions add variables. Let me pause that. Okay, sorry, I was getting a choppy internet feed for a moment there. What I want to say is that when we talk about mutate the joins, we're matching between a primary key and a foreign key we're copying variables between these two tables. So we're going to look at an example here using the mutating join. First, we want to match up our observations by the keys. We've matched up on the keys that surrogate key of year, day, hour, origin, destination, tail number, and carrier. And so we do see the body there. And then, of course, the output of these this relation as well. So when we do the left join, we are including all the left join to flight 2 data. We pull an additional column to our tribble. Because we're doing a left join, we include all the observational data from the flights table, and we include additional table data we match on our composite key. So let's look at the syntax of our left join to another table called airlines. That might be our next table, next screenshot here. Okay. And don't worry too much about the syntax. It can be a little confusing at first. But here we can see the left join to the airlines table, and we're also joining on the carrier between these tables. We add an additional column called name, and we can see in the rightmost column the United Airlines, the JetBlue Airlines record here, or this field in the record. So we're going to go a little deeper into these as well. But let's look at another way that data differs in syntax, but we can provide the same data. We can, this is one way, going between 2 screenshots here. Here we have a left join, but what's unique to ours is this mutate function. We've replaced the left join with this unique R function mutate. We're still matching on the carrier and the airline's carrier keys. Of course, we added that name data to the column. But we do see it's a similar data set in both. So let's look next at visualizing these joins. We're going to have 4 mutating joins as we know in R. We are going to talk about the inner joins, the 3 outer joins, and we also need to talk about what occurs when there is not a match. So let's start with this visualization when understanding joins. Here we have 2 triples that are visualized, each with 2 columns. We have an X and a Y. And we can look at the underlying syntax of these triples with for observations and rows. So we have rows 1, 2, 3, observations 1, 2, 3, 1, 2, 3, the column data. So when we look at the triples, here's some of the syntax here. We have the colors, the green, purple, and looks like a red here. These represent the key variables, the reddish variables, and the gray values, or the green values. These represent the value of our columns. So we can think about this relationship here. This is a kind of the position of identifier and the identified. All right. So then when we talk about joining, we might say, okay, how do we join data for table X and table Y? Well, we're going to want to match up on our keys. So obviously, both these tables have different keys. We can match up the record 1 with the record 1 from table X and table Y. We can match up additionally record 2 with record 2 between these 2 tables. But our last positional record here, 3 and 4, not a match on the key. We're going to have an issue with some of our joins between the X and the Y. So let's talk about the different ways we can join a data. Here we can join data by matching up on the keys like we discussed. Let's talk about what happens when we join data where there is a match between our two triples. Here we're going to look at this visualization here. This kind of has a similar connecting icon. How do we connect data between X table and Y table? We're saying the matching primary key. Additionally, column 1 has that matching primary key. So that's what this dotted line can provide here. But the dot is the number of matches. We can count this. We have 2. We did not get a match from this last one here. And these will be the records that are added to our output. So we've got just a directional arrow here, just an example visualization. But these two records we're getting a match on. And so this would be what we would call an inner join. Let's see if I have any other notes there. All right, so the inner join, this is matching the pair of observations where we have an equal match of a primary key. Sometimes we call this an inner equijoin because the keys match up with our operator. And this is our filtered resultant data set. So the output of inner join is a new data frame, as we see here, with the keys that have matched up in our X and Y values. They are no longer two tables, but one tribble now, one relation has joined them. So the most important thing to remember about the inner join is that the unmatched rows are not included. So you're essentially filtering out records that don't match with a primary key. Inner joins you have to think about when they're appropriate. There's times you're only going to want a set which has inner join data, but of course, because you're filtering records, if you're looking to pull everything, they may not be the best use for your data. Let me go here to the next slide. Okay, so let's talk about the other kinds of joins. Outer joins, full joins. Well, the outer joins, these keep observations that appear in either table. So when we look at an outer join, we are actually going to pull what is here, every record, even if it's not a match. So we're using the same example. In this example, we have data in table X. That third record will pull without any value for the Y column. And when we do what we call a full join on the right-hand side, here we have the null value, the missing value on the X table, but we're still going to pull a third record. It will just be a missing or incomplete value from X, but we will include it because we have a Y value. We also have a full join. So here on our third table, we have basically a container for a record, but we do not have a value itself. So here, this one's pretty interesting. So you have all the inner join data. We have a Y detail where there might have been a missing value here on Y. We don't see a Y3. Or, oh, I'm sorry, it's joining the X data with the not applicable. So it doesn't know how to join these keys. So you're just going to get invalid data, invalid Y data. So that's what we're seeing here. So full join keeps all observations in X and Y. The right observation is going to keep all observations in Y, and the left join will have all the observations in X. So these joins, they work by adding additional virtual observation to each table. That's how you could think about them. And the observation has a key that will match. All right. So we can also think about these joins as Venn diagrams. This preserves, as we talked about the inner join, this preserves the original observations that match, but depending on how we want to pull unmatched data, we may pull just the matching along with left join data, or the matching but the additional right table data, or simply all the data. So visualization kind of thinks about positionally which entity we're pulling data from. Just so you know, most relational database management systems, the default join is going to be the inner join. So you will see that if you just write the word join, it's going to default to the inner. So these can be helpful diagrams when you need to jot your memory or just need to think about how you're pulling the data. So let's talk about duplicate keys. So far, we've talked about diagrams that we assume have unique identifiers. So, for instance, if you go back to our plain example, we might have a plain identifier primary key that's just a sequence of numbers that's unique. But what about in scenarios where the keys are not unique? So you might have a table that has duplicate keys. This is useful when we want to add in additional information and there's a one-to-many relationship. Sorry, I had a little something fall there. But now in this visualization here, we have a slightly different situation where we have our X values, we have our Y values, but we'll see that the key, it's not unique between each record. So with that key value 1, we have 2 X records, 1 Y record, and for value of 2 on the X table, we have 2 records as well with the Y. So this is what we're going to start to see when we have about a one-to-many relationship. We have 1 Y to many X's, and we have 2 different examples of that. And this is an example too, where the primary key might be on the Y, and the foreign key is on the X. So let's take a closer look at that. Here we're looking at the syntax here. We have our 2 tribbles, the X tribble and the Y tribble. We also see how to do this left join between the tribbles using this this by equals key, and you're getting these various matches here. Both tables have duplicate keys, and this is usually an error too, because with this, you may get duplicate keys, you may get all possible combinations, which we also call a Cartesian product. So here's an example of Cartesian product. You're getting every example, x1 with y1, x2 with y2, so down the line. So, and then x2 with y3. So you kind of see this multiplicity here of all the possible combos because there's not a clear key matching between them. So yeah, it's something to consider in your data set when you're doing your validations. So we want to talk about defining the key as well. So far, our pair of tables have been joined by a single variable. That variable has been the name in both tables, and we encode it with that equals key, equals key syntax here. But you can use the ever value by to connect tables. We can show it here if a join. Connect tables in other ways. The default is by equals null. This uses all the variables to appear in both tables, which is also called a natural join. But you might use, for example, like flights and weather tables to match on variables of year and month and hour and origin, kind of we looked in earlier in the presentation. This one here too, looking at this join, let's see if there's any other detail here. We're seeing, we've got a little cutoff here, but about 336,000 observations, 18 rows, and additionally, that character vector by equals, say in this case, C or equals X. When we do by equals X, it's like a natural join, but usually only some of the common variables. So for example, if we have flights and planes that have a year variable, but they mean different things, we only we might only want to work off a tail number, a more unique identifier. Again, it's important to know in our tables what is a unique identifier, because we may unintentionally match up incorrect records. So let's see if there's anything else here we'd want to note. One other thing we want to note is that we may want to combine flight data that contains location, longitude, and latitude of each airport. So we might want to think, how do we join left join two different airports based off their destination? And we may have a flight with an origin and destination of airport, and we may need to specify how we do a join like that. So just thinking about how these tables are going to join together is always critical. You know, even when we're doing self joins as well, just how do we pull data that's matching between the same table but pulling a unique record. So let's talk about other implementations that we can do. Let me just go to the next screen here. Oh. Okay, we have this tool called base merge, which can provide these 4 different types of mutating joins. So we of course have the inner join we talked about, this XY, this end of this package DPLYR, and we have this merge, merge equaling X and Y. So we take advantage of a specific DPLYR verbs. These strongly convey that intent of what we're trying to code. And the difference between the joins is important, but it's not as obvious in the merge, right? Because you don't say inner or left merge. You know, you might have a similar, you know, result set, but sometimes we want to think about the advantages of using a package which clearly spells out what we're looking to get done. Also, the DPLYR joins are considerably faster. They don't mess with the order of the rows themselves. So given that SQL is inspiration for these DPLYR conventions, we recommend that translation, you know, where you might see, I have a screenshot here, you might see an inner join between X and Y here, where in SQL it's, you know, select star from this table, join records to Y using, you know, this key. You see more of a succinct, clear syntax using DPLYR. And you have the various joins, as we said, the left join, the right join, the full join, which pulls all the records. But of course, you know, there's just a lot of conventional tools. Note that sometimes we just drop the full or the inner, especially in SQL, given that they are just implicit. So let's see what we got here. Filtering joins. Oh, so yes, as we just want to suggest one more thing, SQL does support a wide range of joins other than DPLYR, because you connect tables using constraints other than equality, not so, you know, not equal to this or greater than equal to this. But we have been looking at more of the equijoins so far. But just to let you know, SQL does allow for non-equal or non-equal join types as well. But let's talk about filtering joins. Oh, that sensitive mouse. Sorry about that. So let's talk about filtering joins here. Simply put, filtering joins will match observations in the same way as a mutating join, but they affect the observations. They don't affect the variables. So let's look at 2 different types. We have a semi-join and an anti-join. And the semi-join here looks similar type of syntax, but we're going to keep all observations in X, but have a match in Y. The anti-join just drops off all observations in X, but have a match in Y. So we might need to think, why would we use semi-join? Why would we use anti-join? Well, Semi-joins, these are going to be useful for matching filtered summary tables back to the original rows. For example, if we were to look at maybe top 10 most popular destinations for flights, we might want to use the semi-join. We might want to first count the number of records, number of people that flew to Chicago or Atlanta or Los Angeles. And then for each of those destinations, we might want to construct a filter and just see, how many people by year went to this destination. We could break it down by month. So we need to kind of think about our summary of this. But the semi-join, what's unique is that it connects two tables like a mutating join, but instead of adding new columns, it's going to keep the rows in X that have a matching Y. So let me see if I can show this here. This is an example. So we look here, we have a semi-join of those top destinations. We're joining by destination. Here we have the number of records and columns. And we have that, of course, the graphic visual of how a semi-join works. So here, only the match is important. It doesn't matter which observation is matched. It means that the filtering joins never duplicate rows the way that the mutating joins would. So an inverse of the semi-join is going to be called the anti-join. It's a visualization here. These are useful for diagnosing any sort of mismatch. So for example, when we connect flights and planes, we might want to see how many flights do we have that do not have a match in planes. Let's see if I have some syntax here for you. Okay, yeah, so here we have an anti-join. We're going to be joining by the planes, by this tail number. Okay, and so we have our observations here down below of our 722. So here we're trying to see how many of these are not matching. Might be a good validation tool as well. So let's talk about some of our issues that might happen with join. The data we looked at has been primarily pretty clean, but when you're working with real life data sets, you're going to see a lot of data type issues or data that was input from some system, maybe an enterprise resource management system or CRM, ERM, CRM, that is just not going to have the data that's very clean. You might have null data, missing data. So we really need to remember that data in the real world is going to be much more difficult to work with, much more difficult to wrangle. And so we might have to, as data analysts, spend a lot of our time just thinking about how to wrangle that data, how to join it, what values need to be added, which observations need to be removed. So let's think about how we might work with ways to resolve a joining issue. Most importantly, let's identify in a entity, in a table, where are primary keys. So do we understand the data? Do we understand the domain of the knowledge here? We look at the flights table, we're probably looking for some sort of flight number, maybe a tail number. So yes, we want to know in our role maybe what guides we have available to us, what are our sources of truth, maybe what our departments look at. Are we looking at, especially when we talk about like revenue numbers, are we looking at financial data? Are we looking at some sort of projected data? So it's really important to think about, do we understand what the data means? Because we might get lucky and get the right combination of data, but just on the other hand as well, we might have a very similar name variable or something that we believe is going to be the right key to match to another entity, but it might be incorrect. So number one, resolving data problems, let's understand the variables. Second, let's make sure we have observations with a primary key. We start talking about our principles, Edward Deming's ideas about the acid principles, that all database transactions are atomic and isolated, the acid principles that are durable, they stay into the database. So it's really important to think about how this data looks. So here's an example we have of ineffective identifiers. We might be counting the altitude and longitude. This table here with 3 different datas. Yes, altitude and longitude uniquely identify at each airport, but are they good identifiers? Probably not, because you have maybe more of like a coordinate. You might have a period in this coordinate. It's going to be pretty messy. So it might be better to have an additional column created, which is going to uniquely identify which airport we're at, instead of using unique data within the airport data set. So another thing we can do is we can check that our foreign keys match primary keys in every table. The anti-joins can be very helpful as a validation step to pull records that are not matching. And when we find those records that don't match, we can then go back to our original data set, go back to a database and fix this data, especially if it's being input into like a data warehouse or another source of truth. So fixing these issues is critical and it occurs quite a bit. So yeah, when we have missing data, let's be thoughtful about how we use our inner and outer joins. Specifically, if we want to drop records that do or do not have a missing observation. So finally, yeah, we talked about dual aggregation as well. Do we have a count of records? If we have 100,000 data about flights, and we're only pulling back maybe 25,000 records, like a fourth of that, we might think, okay, well, how do I validate? What did I join in where I got so fewer flights? What's being missed? Where are the duplicates? Really thinking about our aggregate number in terms of some summary statistics here. So the opposite is true too. What if your data set doubles? You probably have something doubling that data set, maybe in ineffective join is happening there. So finally, let's talk about some set operations. Set operations, this is going to be useful for working with multiple sets of data, maybe tables that are added together. I've seen this where we've had two different sources of income, maybe cash income and credit card income, that are combined together for a customer. So that's a time where you might want a union of data, returning unique observations for both. That's that second one there. But yeah, you might want an intersection of where you're looking for maybe two conditions, maybe all the customers that had gone to a specific destination country. And so you want just these records of, in table A, this customer within a destination, and that's table B. So let's pull those unique records. Let's use an intersect. Set difference. This is kind of like the order is very important. You may want a table from one set of records subtracting records from a secondary table. So this observation here, we would pull records from X, but not in Y. I think I might have an example here for you. Well, we always want to think about the possibilities here of this data. So yeah, let's a lot of this data, I just want you to remember, this is going to come with time, getting comfortable with SQL and the unique R functions here. But we covered three primary ideas. One is relational data. This is basically the organization of entities, of table data, into moving from just data to information. It's things that people can use, things that our businesses are going to use in business processes and PowerPoints, and make decisions to increase revenue. So we also want to think about relationship data as the adjointment of tables or entities, and also just telling a greater data narrative. How do we, we're not just relating random numbers, we're, pulling in together meaningful information. How do we pull that in? Well, if we're going to have relational data, we're going to have keys. These are unique identifiers that match up entities. We match up records so we can pull another data set, a data set which is going to be our composite. So we may be, we need to think about what is our primary key, which is our identifier on the our primary table, and our foreign key, which is our identifier on a secondary table. And what is the relationship between these two? We talked about how keys might be composites. They might be, not just, there might be not just a flight number, but a year, a month, a day. These things added together to make a composite key. You might have a something that looks like a key but is not. So we may want to look at our relationship database and say, okay, well, kind of get some kind of info statistics about this table. Where is my primary key? Did my developer include that? Do we have a guide on it? So very important to know, what are your primary keys? What are your foreign keys, and our entity relationship mappings should show that. Finally, how do we join the data? Are we joining with an inner join where we pull records from two tables, perhaps a right or left or full join where we pull data which may not exist in one table but exist in another. So we always want to think about directionality. Are we pulling data from a non-matching table on the right or a non-matching on the left, or everything? We might get a Cartesian product where we get all possible combinations of these records which are pulled into a table. There we risk duplication, but we also have the security of getting all the records. So that's something to consider. We also want to consider, is it a one-to-one relationship? When we talk about flights and customers, it's probably not. You'll probably have flights that multiple flights per customer. If you do a many-to-many relationship, maybe many flights to many airports. Well, now we need some reference tables. How do we relate these things together? You might need to have additional detail about like cities or location or personnel between these two. So thinking about, it's always good to put a visualization, a graphic, drawing out what are my tables, what are my relationships between them, how do they join? Looking at your past work too, how's your team sought to create reports to join data together, to pull meaningful columns. Because as we all know, like the data was going to get very complex very quickly. So it's really important that when we build our queries and work in R or SQL, that we're cognizant of the data we're pulling, how we're pulling it, and doing our validations to make sure we are pulling the correct data. Well, it's been great spending time with you. I hope this has been helpful. This should be a good first step into relational data. And the journey, of course, continues through all our learning more, getting practice with the code. And I wish you the best, encourage you, continue with the exercises. And I hope this video was helpful. Signing off here, Greg Talbot. Have a great day. Thank you.